Okay, so the area of a circle is pi r squared, where r is the radius of a circle. There is one circle in this square, and so the area of atoms, or the area of circles in that square, is equal to the area of one circle, which is pi r squared. Okay with that? And times 100 to make it a percentage. Can we simplify this? Yeah. We've got r squared on the top and r squared on the bottom. The r squareds cancel out. We didn't know what the radius was, but in terms of packing efficiency, it doesn't matter what the radius is. If the atoms are arranged in this lattice here, this simple cubic lattice, the packing efficiency is going to be the same regardless of the size of the atoms. So we end up with pi over 4 times 100%. Well, this is not math class. I want an actual number here. Use the pi button on your calculator. Don't shorten up pi. So I've got pi. Where'd you go? It's hiding from me. It's like seriously hiding from me. Don't you hate that when you're staring at something and you know it's there and you cannot see it for the life of you? Okay, my brain fart's over. I found my pi button. Yeesh. So pi divided by 4 times 100. And that gives me 78 and a whole bunch of digits. I'm just going to round it to 4%. Pi, as I use it on my calculator, has a whole bunch of digits, at least 9 or 10. I don't even know how many. The 4 in this equation is exact. And so sig figs, then there would be a ton of them. Do we really care about all the ones after this? No. And I'm not going to try to trick you on that. But this would have a packing efficiency of about 78.5%. Any questions? Yep.
So in this example, you said it's going to be easier because the circles are just 1/4. But another question, the circles are going to be different sizes. That's what makes it harder.
Well, this is easier because it's in 2 dimensions.
Oh, okay.
When it's in 3 dimensions, then it's harder to look at. And then you've got cubes and things, and it just becomes a little more difficult. But the real idea here is just to give you the overall, how do we calculate packing efficiency? It's really just using geometry. You figure out what volume or what area, if you're doing 2 dimensions, is occupied by the actual spheres, and you divide that by the volume occupied by the cube or the square. So that was the simple cubic, the body-centered cubic cell. So here we've got this gold-colored atom in the middle. That is not a different kind of atom or ion. That is the same as the purple ones. We made it a different color to make it easier to look at, so we can see what we're talking about. So here we have one atom in the middle, and again with the eighth atoms on all the corners. Body-centered. So in the center of the cell is the center of an atom body. When we look at this one along the length, the atoms on the corners don't touch each other. There's a gap here. So we can't say that the length is 2 times the radius. In order to calculate that, we have to find a diagonal where all the atoms are touching. And in this one, it's from this corner to the opposite corner. You're going through one atom, that's 1 radius, an eighth of an atom here, and then you're going through this complete atom in the center, so that's 2r, and then through another one. So that diagonal is 4 times the radius. And we can make a right angle with, we're calling this C, where that would be the hypotenuse, and L would be one side, and B would be another, and then you can use the Pythagorean theorem. C squared equals A squared plus B squared, but here we're going to use L instead of A. We know that C is 4R. We just figured that one out. And so then we plug things in and rearrange them. Again, I'm not going to make you derive this on an exam. The bottom line is the length of the side is equal to 4 times the radius over the square root of 3. It's a seemingly random little equation, but it just comes from three-dimensional geometry. Any questions? So here again is that unit cell. If we look at it with all of the corner atoms in full, we see it looks like this. And then here, we're expanding that so that we can look at how many atoms does this corner atom touch directly. It's going to touch 8. So the coordination number is 8 instead of 6. It's gone up. And the packing efficiency has also gone up. It's 68%. You could calculate that, but we're not going to. Any questions? So an atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? What we need here is this guy. Yes. I'm just so fed up with the pointer here. We need this. I'm not going to make you memorize that one either, right? It'll just be hiding on this big sheet of equations. You got to know how to look for it and pick it out. So L equals 4R over the square root of 3. So let's write that down before it leaves our brains. L equals 4R over the square root of 3. What is the volume of the unit cell? It can be really helpful to draw little pictures for yourself. So the unit cell is a cube. You don't have to draw the circles and parts of circles inside. The length of each side is L. What's the volume of that cube? L cubed. Length times width times height, they are all L. So the volume equals L cubed. They're asking for the volume of the unit cell. This is what L equals. So the volume is equal to 4R over the square root of 3 to the third power. What's R? R is the radius of an atom, right? So here the radius of the atom is 138 picometers. What unit does it want us to give the volume in? Cubic centimeters. So you have a choice. You can convert picometers to centimeters, or you can wait till the end and convert cubic picometers to cubic centimeters. So I think it's easier to do it before we cube the thing. So I'm going to do that down here. There's different ways you can do this. So 138 picometers. We want to get it into centimeters. So picometers to centimeters, both of those units have a prefix. So we have two prefixes. It's best to do this in 2 steps. So I'm going to convert from picometers to meters and then to centimeters. There are shortcuts, and you can use those if you wish. I'll show you one in just a minute. Picometer down here, meter down here, so the units work out. What does pico mean? 10 to the negative, not 9, 12. 10 to the negative 12. So 10 to the minus 9 is nano. Nano, 9, you go together, right? Most of them, except for centi and deci, are factors where the exponent is a multiple of 3. So minus 3, minus 6, minus 9, minus 12, minus 15. So that kind of limits the amount of guessing. So that's what pico is. And then centi is 10 to the minus 2. So you can do this, using the calculator. 138 times 1 EE minus 12 divided by 1 EE minus 2 equals. And my calculator shows me a bunch of zeros and 1 4. The number 1 and the number 4 at the very end. But we're just multiplying and dividing by tens here. This should still be 138. Your calculator's kind of tricking you, so you need to trick your calculator. If you put it into the mode where it shows all numbers in scientific notation, it'll show it to you correctly. If you're not sure how to do that, come and ask me during lab and I'll show you. This is 1.38 times 10 to the minus 8 centimeters. Another way you can do that, kind of a cheater way, is 138 picometers, right? So instead of writing the prefix pico, I'm going to put in the 10 to the thing that it means. So I'm going to take out the pico. Pico means times 10 to the minus 12. So that's 138 times 10 to the minus 12 meters. That's not proper scientific notation, but your calculator's okay with it. So then we can just convert meters to centimeters. And this you can actually do in your head if you understand dividing by powers of 10. You just subtract the exponents, and so you end up with 138 times 10 to the minus 10. Again, not proper scientific notation, but your calculator will be fine with that. Or if you put that in proper scientific notation, it's going to be 138 times 10 to the minus 8. It doesn't matter how you get there, as long as you get to the right answer. Okay? So we're going to take this and put it in for R. So we've got 4 times 1.38 times 10 to the minus 8. Divided by the square root of 3, the whole quantity cubed. So on my calculator, I'm going to do 4 times 1.38 EE minus 8 divided by, I'm going to do the square root button, 3. I'm going to press equals, and then I'm going to press the X to the little square button and put in a 3 there. And I'm thinking this is going to have 3 significant figures, so this is going to round to 3.24 times 10 to the minus 23rd cubic centimeters. Anybody else get that number? That's a really small number. Is that okay? What are we finding the volume of? A unit cell. How many atoms are in a body-centered cubic unit cell? 2. So 2 atoms, this should be crazy small volume, right? In centimeters cubed. So we're okay. Any questions? Face-centered cubic. So here when we look at this cubic unit cell, on the face, on each face, we have the center of an atom. Body-centered cubic, in the center, of the whole thing was one atom. Here we've got them centered on the faces. And so then we can go through the geometry again, because on the side here, these corner atoms are not touching. To calculate the length of a side in terms of the radius of the atom, we have to find a diagonal where all of the atoms are touching. And so here we find that along the face. B here is equal to 4r. And we can make a right triangle there where each side is L. And so you can go through the geometry here and you end up with L equals 2 times the square root of 2 times r. So L equals this. Any questions? So here's what we were looking at there. This cell contains the equivalent of 4 atoms. You've got 1 atom from the corner pieces. 8/8 of atoms is 1 atom. And then you have half of an atom on each face. There are 6 faces, and so that's 3 atoms. So you get a total of 4 atoms in the face-centered cubic. Here's the illustration showing all of them as spheres instead of cut away, and you can tell that looking at that, you're like, what the heck are we looking at, right? It's hard to see. Expanding that, separating them apart so we can see what's going on, you can look and find out that this has a coordination number of 12. So each atom is in direct contact with 12 other atoms. It's a higher coordination number, and the packing efficiency is going to be larger. Here it's 74%. Okay, another problem. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. There are so many different types of questions I could ask you relating to volumes and packing efficiency and different things. I can't cover all of them, and even if I did, you wouldn't be able to remember them all. This is why it's important to be able to think critically about a problem and figure it out. So what do we do here? Well, we read the problem, we've got a number in there. What are we trying to find? Density. Well, do we have an equation for density? What is density? The mass divided by the volume, right? Density equals mass divided by volume. Well, we're not given a mass, we're not given a volume. We're given a radius of an atom and the name of a unit cell. Well, earlier we calculated the volume of a unit cell, right? So we could do that again. Now this one kind of messes with us because here we're talking about a body-centered cubic unit cell when we just discussed the face-centered, okay? So we have to use the correct length. So the length of a side is 4r divided by the square root of 3, right? And the volume of that would be 4r over the square root of 3 cubed. We just did a problem like that. But the length was 138 picometers instead of 125. So can we calculate the volume of a unit cell? Yeah, we could do that. Volume of the unit cell. How would we find the mass of the unit cell? Could we find the mass of one chromium atom? Yeah. How many chromium atoms are in one body-centered cubic unit cell? 2. So the mass of the unit cell would be equivalent to the mass of 2 atoms, and the volume would be given by this equation relating to the radius of the atom. So thinking ahead, we can save ourselves some unit conversion grief. We want grams per cubic centimeter. So again, we want to calculate this volume in cubic centimeters instead of in cubic picometers. So this 125 picometers. Well, that's the same as 125 times 10 to the minus 12 meters, because pico means 10 to the minus 12. And then we can convert that centimeters to meters. Centi means 10 to the minus 2. So this is going to come out to be 1.25 times 10 to the minus 8 centimeters. So we can plug that in here. And we're going to get, again, some crazy small number. 4 times 1.25 EE minus 8 divided by the square root of 3. I'm pressing equals, and then I'm going to raise that to the third power. 2.4056. 2.40. There's my 3 sig figs. 5, 6 times 10 to the minus 23 cubic centimeters. Did I do that right? Nobody's disagreeing with me, so we'll go with it. One of the suggestions on my faculty evaluation was that I should be more Socratic in my teaching method, which means I should ask more leading questions. The problem with that is that if the students don't answer any of the leading questions, you end up with really long, awkward silences, and you waste a lot of lecture time. Okay. So how do we find the mass of 2 chromium atoms? I need some space. I'm going to do this up here. Well, 2 atoms of chromium, I want to end up with grams. What does the periodic table tell me? It gives me the mass in grams of what? A mole. So I need to figure out how many moles is 2 atoms. We convert to atoms to moles. We know that 1 mole is 6.022 times 10 to the 23rd atoms. So that gives me 1 mole. Well, it gives me a chromium in moles. And then I look at the periodic table. For chromium is 51.9961. 51. Short-term memory's like gone. 9961. Grams per mole. So I can find the mass of 2 atoms. This is going to be a really, really small number. .72. 2 atoms is exact. Avogadro's number here has 4, so that's what's limiting the number of significant figures here. 687 times 10 to the minus 22 grams. So I plug that into my density equation. 1.72687 times 10 to the minus 22 grams. And you put in those messy, messy numbers, you come out with 7 point stuff. This would have 3 sig figs, so 7.18. The units are grams per cubic centimeters. we took those two crazy messy numbers and we got 7. Is 7 grams per cubic centimeter a reasonable density for a metal? Yeah, metals are generally more dense than water. Water is 1 gram. Hey Siri, what's the density of chromium?
Chromium is a chemical element with symbol Cr and atomic number 24. It is the first element in group 6. Would you like to hear more?
No, thank you.
Done.
So she showed me, she didn't tell me what the density was, she didn't read it to me, but she showed me. So what she pulled up said 7.14. Is that close enough? Yeah, it is. Because we kept track of our sig figs here, there's uncertainty in that second decimal place. And so the fact that it's a few digits different is fine. Any questions? So you can actually calculate the density if you know how the atoms arrange themselves and what size the atoms are. Or if you measure the density, which is a lot easier to do, and you know how they arrange themselves, you could calculate the radius of the atom. So another way to look at these crystal packing structures is to think of stacking the atoms up in layers. So this is what really reminds me of packing fruit. If you pack fruit, you put one layer of oranges down and then you put another layer on top, right? You could try this at home with fruit or with marbles or tennis balls or something. Get a box and see what happens when you put round objects in there. So the simple cubic structure is one where you have a layer of atoms where the atoms are arranged in a square pattern, and the second layer of atoms is directly above the first layer of atoms. Okay? There's a lot of empty space. Marbles, tennis balls don't want to do this in a box unless you kind of force them to do it. There's a lot of empty space. It's not the closest way to pack them. So this is not a closest pack structure. That's a simple cubic structure. More efficient packing on that base layer is to take one row of atoms, and the second row of atoms you're going to offset by half an atom. So instead of this atom being down here in a line with this one, it's going to be between them. And that's going to nestle closer together, and this empty space is going to be smaller. Does that make sense? So we'll do that for our first layer. And then the second layer, instead of putting them directly on top so that layer B is directly over layer A, we're going to let that layer B slide over and be offset and fit into those indentations. And that's what spheres in a box will naturally want to do. There's like a little divot here between these 3 atoms, and the next layer is going to want to sit in that divot because it's lower in energy. It's lower in potential energy. So here we have an AB pattern. The next layer would be directly above layer A. So 2 different closest pack structures. This one that's called hexagonal closest pack, you have layer A, layer B is offset, and the third layer is layer A. Again, it's directly in line with the first one. That's called a hexagonal closest packing structure. It has an AB pattern. The unit cell here is hexagonal, it's not cubic. So here's the first layer, the second layer, and the third layer directly lined up with the first layer. So cutting this up, we see this is a hexagon. It's not actually the smallest piece, though right here is the smallest piece. That's a unit cell. The angles here are not 90 degrees for everything. So it's a hexagonal thing. The other closest pack is called cubic closest packing. So here we have layer A and layer B again, but now layer C, instead of lying directly over A, is offset from layer A. We've got an ABC, ABC pattern. This is actually identical to a face-centered cubic unit cell. And that's not hard to see at all. Oh wait, yes it is, very hard to see. So here we're looking at how we're packing the layers together. So here we have layer A, layer B, layer C is not the same as either A or B, and then we've got a fourth layer on here. So put those chunks together, put them on their side sort of, tip them over like this, and then shave them off, cut them down, and that's our face-centered cubic cell with right angles. Any questions? Is your mind like rebelling yet?